I'm very happy to be here. I am Alex's youngest graduated student, and I wanted to. I think I am.
Oh, maybe you didn't get it.
No. He takes time. And I think, and I wanted to say a few words, mainly that being a student of Alex is very rewarding, and he's very special to me, and I think to all of his students, in the sense that he cares about us. I know that he cares about our well-being even more than about our mathematical achievements, and he really cares about our mathematical achievements. And it was always, I always felt a great sense of privilege to be Alex's student. And today I'm going to give a talk which would be a bit more on the Midrasha style. I want to tell about the history of Golden Gate and high-dimensional expanders, so I hope for some of you it will be interesting. So we'll start with Ramanujan graphs. So Peter and Alex and Phillips wrote 3 papers around the 86, 88. And one of these papers became a major hit, and 2 of them went a bit unnoticed. And I think they realized a few years later that it's all about a catchy title. Ramanujan graphs is very catchy, and Hecke operators and distributing points on the sphere part 1 is much less catchy. I think today they know this. And I want to tell a bit about the story and how these papers connect to each other and what happens, what are the developments today. So things begin with the hyperbolic plane. Grigorchuk told us a little about, Rabinchuk told us a little about this. So you take the group PGL2R modulo a maximal compact subgroup, you get the hyperbolic plane, and the spectrum of the Laplace operator, which are the frequencies at which the hyperbolic plane as a drum oscillates in the entire ray from a quarter to infinity. And then Selber's conjecture was that if you take quotients of the upper half plane by arithmetic lattices, so things like PGL2Z, you should get surfaces which spectrally behave like the upper half plane. So the spectrum of the Laplacian on the surface, on the upper half plane modulo the lattice, should still be in the same ray. And Selber's theorem was not a quarter, but 3/16. And as we know, no progress has been made on that for more than 50 years. No, I'm joking. I think people know. No, everybody knows. So there has been progress, but going back to the 80s, this was the first attempt of Alex and Peter to construct expanders. And this can be used to build expanders. So you take these Riemann curves, these surfaces, and you plot graphs on these surfaces, and they show that you get expanders. But luckily for them and for us, these expanders weren't as good as ones that were already known. So they had to push it further. And their breakthrough was when they replaced the real group by a p-adic group. So they replaced PGL2R with PGL2QP. And still you take a maximal compact subgroup and you look at the quotient. And the quotient is, in a sense, which I will explain, a regular tree. So I don't know who to attribute this to, maybe Tits. I don't know if, historically, who realized that this is a combinatorial object.
Ihara in an explicit way, I think, but probably Bruhat-Tits.
Yeah. And what Peter and Alex realized, that they can do things here much better. They don't need to plot a graph on a surface. They already begin with the graph. And so the idea was that quotient of this tree by arithmetic lattices in the p-adic group should behave spectrally like the tree. So here the spectrum should be like the upper half plane, and here it's like the tree. And the spectrum of a tree, the adjacency on the tree, is -2 square root p to 2 square root of p. This was done in Harry Keston's PhD thesis. I think he was the first one who explicitly computed this. And even better, what replaces Selberg's conjecture is the Ramanujan conjecture, which was actually proven completely in this case. For what Alex and Peter needed, it was done by Eichler, and in greater generality for Deligne. And this gave them Ramanujan graphs. So I want to explain how this, what happens here. So we need to construct an arithmetic lattice in this group. And when you start learning p-adic numbers, you get the exercise to show that Z1 over P is a lattice in R cross QP. So it's quite easy to show this thing, and then you take a leap of faith and believe that and accept that PGL Z1 over P is still a lattice in PGL R cross PGL QP, or you can actually work this out. But the thing is, it's not a lattice in the p-adic group alone. If you look what happened in the p-adic place, it's not a lattice anymore. So you need to do something else to get a lattice, and the trick is to pass to unitary groups. So I'm going to use the group of unitary similitudes. It's not exactly the unitaries, it's very similar. So unitary matrices are matrices such that A star A is the identity. I'm also allowing A star A to be a scalar matrix. And eventually I'm looking at the projective group, so I'm dividing by scalars, so it's more or less the same thing, but it's nicer. And R here can be any one of these rings, so we'll take the real, the p-adic, rational, and finite fields. And again, the PGU Z1 over P is a lattice in PGU R cross PGU QP. So PGU 2R is the unitary group that you learn about in first year linear algebra. And this is, you imitate the same thing formally over QP. But this time, this group is also a lattice in PGU to QP alone. And the reason is that this part is compact. This is the unitary group, it's compact. And when you kill this part, you think about a lattice here, then you project it to this component. And because you projected from something compact, you're still discrete. But now you have a lattice in PGU. So you need to work a bit more, and you need to use Jacquet-Langlands. And the Jacquet-Langlands allow you to take Ramanujan's conjecture from PGL2, what Eichler and Deligne did for PGL2. Alex and Peter could use Jacquet-Langlands transfer to show the same, that Ramanujan conjecture hold for this other group. And then if they take arithmetic group, so for example, congruent subgroup, so subgroup of this lattice which comes up as a kernel to finite group, they have eventually finite graphs, and these are Ramanujan graphs. So this is the XPQ from Alex and Peter and Philip's paper. And you probably never saw it presented as PGU, and the reason is that eventually PGU and PGL are the same over the p-adic. They're isomorphic, except for P equal 2, which nobody likes in any case. So eventually you'll see this statement. Now, I think more or less everything I said was done independently in parallel by Margulis in the US, in USS, in Russia. It's in Russian, so I couldn't verify the details. But they had very similar ideas, but here something different happened. Alex and Peter were in touch with actual combinatorists, and combinatorists were actually looking for explicit expanders. And the fact that some double coset space of p-adic analytic Lie groups is a Ramanujan graph did not make them happy enough. So they wanted to give an explicit construction, and they managed to do that. And this turned out to be very successful for other purposes, which I will get to later. So to understand where it comes from, I want to tell you a bit more about this tree. So what is the Bruhat-Tits tree? Let's start by recalling what is a Schreier graph, which if you don't know what it is, you shouldn't be sitting here probably. You take the cosets of a subgroup in a group, and you connect two cosets if they are translated by some fixed set of generators. Now, the Bruhat-Tits tree is not the Schreier graph of PGL2QP with respect to the cosets of PGL2ZP, which is a statement that I heard people saying. This is not what happens. What happens is something I couldn't find a name for, so I call it a Hecke graph. It's very similar. The vertices are still cosets, but the edges, instead of connecting GK to SGK, you connect it to GSK. It looks quite harmless, but it's a big difference. And notice that this thing is well defined as you see it, but here, if you multiply G by some element of K, you're still at the same coset. So now you need to connect GK also to GKSK. So when you look at this and you look at the set S, you don't see immediately what neighbors are you connecting to. So the Bruhat-Tits tree of PGL2QP is the Hecke graph of G, K, and basically any integral element of norm P will get you a tree, the Bruhat-Tits tree. But if you want to know explicitly who you're connecting to here, then you have P plus 1 neighbors, and every coset connects to P plus 1 cosets, which I think most of you saw in one context or another. But this, you need to work to show these things. And here it's how it looks. So for example, for PGL2Q2, K is PGL2Z2, and here is the explicit set of generators. Every vertex connects to these three translations, but these are translations from the right, and then you also act by K. So you can stare at this image for quite some time, and I actually did it. And it's fascinating. Now, this thing is, as I said, it's not a Schreier graph. In particular, it's not a Cayley graph. And what Lubotsky, Phillips, and Sarnak did was to give this thing the structure of a Cayley graph. So, of course, you can give any regular, well, it's a regular tree, it's a Cayley graph of a free group, but they did it inside the arithmetics. So here is our tree, GK, and these are the edges. And we can think about this tree as coming from PGL to QP or from PGU to QP, because we said they're isomorphic, and we have inside this lattice. What they showed was that for P, which is 1 modulo 4, if you take the second congruent subgroup inside this lattice, so matrices which are congruent to 1 mod 2, this subgroup acts simply transitively on the vertices of this Hecke tree. In other words, this congruent subgroup is a transversal for the left cosets of K. Every coset contains exactly one element from this congruent subgroup. And there you have a question. And this tells you can identify the vertices, the cosets, with the element of gamma 2. And what happened to the neighboring relation is very nice. Earlier we had GK connected to GSK, but now we have this representative from the transversal, some gamma. And if you make sure that S also comes from gamma, then suddenly you don't need this K anymore. You just have S acting from the right. And this is exactly a Cayley graph, but it's a right Cayley graph. You started everything by doing action from the left, and somehow you got here eventually a Cayley graph acting from the right. Now, what are the generators of these Cayley graphs? Actually, I didn't tell you how did they prove that, and this relates to what are the generators. The generators come from number theory. They come from Jacobi's 4-square theorem, which tells you that there are 8 P plus 1 solutions to writing P as a sum of 4 squares. And let's do the following. Take this and write it in terms of Gaussian integers. So A plus BI, C plus DI. And look at this matrix. This is a matrix which sits in this lattice. So it's quite easy to see that the rows are Hermitian, unitarily orthogonal with respect to the Hermitian inner product, and this matrix times its transpose is P, which is invertible in this ring, which is what we need. And you work a bit further, and you show that inside the congruence subgroup, only 1/8 of them are in the congruence subgroup. So you get eventually P minus 1 elements in the congruent subgroup of determinant P. And these are your generators. So for example, let's take P equal 5. So you're expecting 6 generators in the congruent subgroups, and here they are. And they appeared yesterday in Peter's talk as the V-gates. So this is what the quantum computing people call these. But you can do it for any P, which is 1 mod 4. And so what we did here was we gave the Bruhat-Tits tree an explicit structure as a Cayley graph of the unitary group with respect to this generating set coming from the arithmetics. So what we got here is one corollary is that gamma 2 is a free group, because if its Cayley graph is a tree, then it means it's free. And we got the LPS graph, these Ramanujan graphs are actually Schreier graphs. So earlier we had double coset spaces with the action of S squeezing here annoyingly in the middle. And now we got rid of K, we replaced G mod K by gamma 2, and S acts nicely from the right. So these are really Schreier graphs, and actually they're also Cayley graphs, because you take congruent subgroups, so gamma 2 mod gamma 2, gamma 2Q is again a group. And what group is it? So it is PGU2 or PSUFQ. This is according to the Legendre symbol of your P and Q, and usually you'll see, and always you'll see this in the literature as stated for PGL2, because this is PGU and PS and PGL are the same over any finite field. Okay, so this is the story of LPS, and then Alex's first PhD student, Moshe Morgenstern, which I think didn't came today, extended this thing very nicely in positive characteristics. So he constructed lattices which act simply transitively on the vertices of the Bruhat-Tits tree of the projective general linear group over the field of Laurent polynomials over a finite field. And he could do it for any prime power, which is very nice. And this paper is always quoted, but I think very few people actually read and saw what happens there, because it's not trivial. Any of these constructions is not trivial. And then to get Ramanujan for these things, he replaces the Ramanujan conjecture by Drinfield's work on the analog properties in positive characteristics. And then a few years later, Peter with Davidov and Valette came back and did the same thing for PGL2QP, where P is any prime. But I think you didn't have prime powers, right? Only primes. But you did do 3 and 2 mod 4. Give a Cayley structure. So it should be noticed, because you all heard about the golden gates, that these things are a bit problematic. Okay, I'll get to that in a moment. Golden gate. So this is quite recently there's been a surge of interest in these results in the other paper of Lubotsky, Phillips, and Sarnak. And this is the context. You have this ring, and we started with this ring, and this is also a subring of R. So we can embed this in the real group, which until now we kind of forgot about. We said we'll kill this part. Now we actually project to this part, and PGU2R is what you call the projective unitary group. So now you can look at gamma 2, which is the congruent subgroup of this arithmetic lattice, and you're getting a free group which sits inside PU2 on P+1 generators, and then they use strong approximation, which is this, to pass things from the p-adic view of this group to the real view of this group. So ignore for a moment the middle. Here I have gamma 2 acting on the real unitary group and on the Bruhat-Tits tree. But we said that this guy acts simply transitively on the Bruhat-Tits tree. So this kind of kills this guy, and you're left with PU2. So if you just ignore the middle, then it seems quite simple. But the thing is, you look at the diagonal action, and this allows you to move operators from here to here. And in particular, the adjacency operator on the tree which correspond to the generators of gamma 2, transfers here to the operator on functions on the unitary group, which sum the translation by these generators. So they have this averaging operator on L2 function on the unitary group. And what, in this case, I think they need here the full Ramanujan conjecture, which is the work of Deligne, to show that, again, the spectrum of this averaging operator is the same spectrum as that of a Ramanujan graph. And they show, again, that this is optimal. And from this, they can conclude that this lattice not only sits densely inside PU2, but that it spreads there essentially optimal. This is what Peter was telling you about yesterday. And the other thing that you get here is the ability to decompose words. So if you just take any group, and with generator, you don't know how to take an element in the group and write it as a word in the generators. But in this case, we understand this group very nicely. It's a free group with explicit generators. So when you're given a matrix like this one, you can check very easily that this is a matrix in this 5 arithmetic group. And now we want to decompose this in the 6 matrices that I showed you earlier, the V gates, and we can do it by going to Q5. So you replace this I, this complex I, you replace it by the square of -1, which sits in the p-adic field in Q5. You get a p-adic matrix. There you look at the action on the Bruhat-Tits tree, and you navigate back to the origin. You get the unique shortest decomposition as a word in the generators. Okay, the actual computing, quantum computer people don't like these gates. They like the Clifford+T gate. So you heard yesterday that the Clifford group is a finite group of order 24, and this is the T gate. And these are all matrices in the unitary group over Z when you add the inverse of the square root of 2. And then there is a very beautiful work of Kliuchnikov, Maslov, and Mosca, which show that this actually, they generate the full S-arithmetic group. So a matrix here can be written with these generators, which is not trivial. And they have one clear advantage over the V gate coming from Lubotsky, Philip Sarnak, is the fault tolerance that we heard about yesterday. You need matrices of finite order to be able to implement your quantum computer in a fault-tolerant way. But they have a disadvantage that the growth rate is far from being optimal. You remember that the gate you get from LPS generate a free group, so you get as many elements as you can hope for. But whenever you have a free group, you'll never have a finite order element. So you need to make some compromise. And we have our new construction, so this is joint work with Peter, is to find lattices which act simply transitively not on the vertices but on the directed edges on the tree. And then we get fault tolerant. We get generators which are of finite order, but we have structure, this time coming from the structure of the edges of the tree. So for example, here is one such gamma. This guy acts simply transitively on the edges of the tree of PGU2 with respect to this p-adic field. So Q square root of 2 completed at square root of 2. And this group has a finite index in the Clifford+T group. So you see that it means that the growth rate is more or less the same, but this guy has 3 generators and this guy has 25 generators. So in terms of efficiency, this is clearly a winner. And then the best we can do, oh, sorry, before that, so what do we get related to the structure of such a group? So this is a very nice structure. All our examples have the following properties. We have a C and T, a finite group and an element, such that the finite group fixes the origin of the tree and acts simply transitively on the neighbors of the origin. And T is an involution which flips some edge touching the origin. And now this implies quite easily that the group generated by these acts simply transitively on the edges. And then it's an exercise in Basset theory to tell you that this means that your group is actually the free product of C and the involution. And you can navigate by the action of the group on the trees. So what it does is you have an edge, then C, the action of C rotates this edge around its origin, and T flips it. So if you want to go from one edge to another in the tree, there's only one thing you can do. You need to rotate it to that direction, then flip it, then rotate it, flip it. And that's the only way you can get to where you want to. So we have, again, optimal navigation. Now, here's something that I like, and Peter is not excited about, but I think it's nice. If you take these elements, so you take the involution times all the elements except the identity in C, this generates a free semi-group. And when you look what happens on the tree, it takes your edge to the edges which leave its tail, and then to the one which leaves that tail. So you're looking at a non-backtracking walk on a tree. So, and this tells you are in a free semigroup, and with a non-backtracking walk, you never get back to where you started. And another nice subgroup is you can take what's generated by all the conjugate of T, and this gives you a group which acts simply transitively on the vertices. You get a decomposition of your group as a semi-direct product of a group which acting simply transitively on the vertices and a finite group acting on the edges. So a lot of structure, and you can get, and by this free product, you get optimal growth under the restriction, and you can identify again the operators with operators on the edges of the tree. So how am I doing with time?
20 minutes.
20 minutes, okay. So let's start to wrap it up. So the best thing we can do is this cool example that Peter showed you yesterday, which has Klein's icosahedral group as the finite group. And it comes from a fantastic ring, the ring of Icosahedral, which was studied by Tits, by John Conway, by Moody. And this ring, well, I wrote it here in terms of quaternions, but you can project the quaternion to the unitaries. And this is the maximal order of the quaternion algebra, the standard quaternion algebra, over the golden field. So this is golden again. It has a unique decomposition, unique factorization. It forms the E8 lattice with respect to some weird inner product on the Icosians. And Peter conjectured that this should be useful for fault tolerance as well, right? It seems to be nice. And what we had to verify is that indeed the icosahedral group acts simply transitively on the, not the origin, on the neighbors of the origin of the 60 regular tree of this p-adic field. So 7 plus 5 phi is just a prime factor of 59 in this field. So this is where it comes from. But it actually happens. I was quite amazed when I did the computation. And as Peter predicted, it really does this. And this is the same thing as PGL2 Q59, but you have to do it like this. And indeed, this T here is an involution, which flips an edge at the origin. Everything works nicely. And in fact, what they generate is the full 7 plus 5 phi arithmetic.
Do the computations, and if you have a group of order 6T, and that's the exact stabilizer that fixes a point,
No, it
must act transitively on the 60 neighbors, isn't it?
if you know that everything together acts transitively on the group, on the graph, but maybe it doesn't. So if you add some consideration of I mean, you can probably replace it by some mass formula if you know something about the structure of maximal orders in this quaternion algebra, you know class number 1. In general, there's no...
if you know this is the stabilizer,
right.
then the stabilizer order 60 and it's not greater than that.
No, but you could have several orbits in the neighbors.
But if the group is order 60, if you have several orbits, then stabilizer of the middle point is
what?
bigger. Okay, that's not
the most important thing is that this local calculation that you're talking, which you check, becomes part of that this sits in a maximum order. That's a
No, Alex, how do you know that the stabilizer is trivial for each of the neighbors? You could have 2 orbits and each one non-trivial stabilizer. I don't see it, but... And I like computing things, so you know that. So.
Yeah.
Okay, so, and eventually what you get is the full 7 plus 5 phi arithmetic group. You don't need to zoom into a congruent group, which also in some sense tell you you're not wasting anything. You're taking the full things and you get what you want. Okay, so one thing that interested me is what do we get when we pull this back to the Ramanujan graph side. So now we have an identification of the edges of the tree with an arithmetic group. And we can take these are the semi-group generators. And if we look at the Cayley graph with respect to the semi-group generators, we can encode the non-backtracking walk on the tree or on a Ramanujan graph as a simple random walk on the Cayley graph of this group and its quotient. And this seemed to me very weird when I had this idea that I can have a Cayley graph behaving like a non-backtracking walk. So I went and computed this, I just said I like computing things, and it really works. So you can get here a Cayley graph of PSL2 F13 with respect to 3 matrices coming from the Pauli matrices. And I think some of you definitely should recognize the spectrum of a non-backtracking walk on a Ramanujan graph with the trivial eigenvalue, the circle at radius square root of the degree, and the plus minus 1, I think. Hyman should also know this. Several of you worked on these things, and here is an example with the bipartite case with F17, so the Legendre symbol is minus 1. I think it's nice. I don't know what to do with these graphs, but I was very impressed. It was kind of a confirmation that everything we do is kosher. Like, oh, I can't cheat. Okay, and now I'll say a bit about what happened when we generalize these things to higher dimension. So as Alex's friends and students know, he liked to share his life wisdom with people. He has many life wisdoms. And this is one which I never quite got. So Alex told me that generalization in mathematics is like violence in soccer. I don't know what, this is one thing I still don't, I hope one day to understand what you were talking about. We'll talk about this. But in any case, in the context of generalizing Ramanujan graph, Alex has been pretty violent in the last decade. And his idea, not only his, was that we want to look at the Bruhat-Tits building of higher dimension. And this is a contractible simplicial complex. And several people had the idea that, okay, the generalization of Ramanujan graph should be the quotient of this complex. So we have Cartwright, Solezhuk, Winnie Lee, Lubotsky, Samuels, Vishne, Salviniazi. And all of them had the same idea that these should be complexes which spectrally behave like the building, and we should be able to construct them from arithmetics. So this uses very deep results from automorphic representation theory. And I write caveat because things are not as simple. So you need to, not everything you'll take will work. And people still don't understand what is the general way to construct Ramanujan complexes in general dimension. And Alex is very persuasive, as you know, so many people thought about the idea of Ramanujan complexes, but Alex, I think, was the one who kept pushing this idea and convincing people to work on it. And today we have a lot of interesting combinatorial properties of these complexes. So we have a celebrated work of some very prominent and I think promising mathematicians showing that these complexes have geometric overlap property, which you heard about. And we have Costa, which is another student of Alex and myself. We did the work on the Chigger constant, and Costa and Shai with Alex did the work on chromatic bounds. And then there are the exciting work on topological overlap, which you heard about. And now we have a new work with Lubetsky, not Lubotsky, but I like Lubetsky, Lubotsky, and Parzanchevski. One day you'll have to practice this, Peter. We show that you have a cutoff phenomena for some random walks on these complexes, which is generalized what Eyal Lubetsky and Yuval Perez did for Ramanujan graphs. So now we have a strong reason to believe that these complexes are interesting. Now I want to show you, if you don't know what are buildings, so everybody knows what a building is? Who doesn't? Who never saw a building? I want to show you how they look. So when you build a tree like this, you start with your favorite V-gate, your LPS V-gate, but you take only the diagonal ones. So there are 2 diagonal ones among the 6 gates, and you get a line. But then when you add the other one, the other generators, at every point you actually have 6 branching. So this is the original branch, and then you have 4 more. But then from each vertex you can branch again. And in this way you get a tree. And from this point of view, it's it's nice to see what happens in higher dimension. So this is the line I showed you earlier. This is I wrote alpha for 1 plus 2i, because then you see that what you have here is alpha and alpha bar. And when you go to PGU3, you just get a plane instead of a line. And you get everything here from the diagonal matrices. The diagonal matrices look like a plane. I made this presentation for a workshop in quantum computation, and when I showed, and people there actually looked at these matrices and tried to understand the algebraic structure of this group, but without the Bruhat-Tits theory, without the p-adic view, it's a real mess. And when I showed this picture, people were like, "Oh." So this is the Bruhat-Tits building in dimension 2. And then you want to ask, okay, so this is the plane is the analog of the line, and what happens around the vertex? So in the tree, this is what happens around the vertex, and in the building, this is what a vertex sees. So now instead of branching of edges, you have branching of triangles. This triangle branches to 2 more here, and then each one to 2 more here, 2 more here, and you get some combinatorial arrangement, which is in this case the Fano plane, because this is what happens over Q2. So I think whenever I think of a building, I can only think about either this, which is called an apartment, or what a vertex is. And I hope one day to understand more. And now the question is explicit constructions. Do I have a few minutes? So how can we do things explicitly? And not talking about the quotient of a Bruhat-Tits building by arithmetic subgroup. We would like to have generators, because these generators on the one side allow us to give explicit construction for Ramanujan complexes, but on the more interesting side, they allow us to transfer things to the unitary settings and to embed our building as a building sitting in the unitary groups. For example, this thing in U3. And use all the combinatorics and algebra of the building in the unitary settings. So this is what we set to do. And of course, you start with Jacobi's 6-square theorem, because now we're in dimension 6. And Jacobi already worked everything out. There are 12 p square plus 1 solutions to the same equation in Zi. So these are the sum of 6 squares, which is very nice. So, but then we get stuck, because when we did this with PGU2, after we found alpha beta, we put alpha beta and then minus beta bar, alpha bar, and we had a unitary matrix. And now what do? I have this first line, but I don't know how to compute it. how to complete it to a matrix with determinant P. And this is quite frustrating, so I actually sat down and tried to do it. So here is a matrix coming from P equal 5. So here the sum of square is 5. And I tried to understand how do I take this first line and do the same trick with the alpha beta, moving things around to make, I need two lines which are orthogonal, Hermitian orthogonal to the first one, and among themselves, and sum to 5. And you can work out how to do that, but then you do the same thing for 13, and you work it out again, and then you do it for 17, and it, you find what happened. But when you get to 157, there is no hukiyut, how do you say?
There
No.
is no simple algebra whose determinant is equal to the...
Wait. I don't know, by the way, for this unitary group, whether there is. But we'll talk about this. So at this point, I kind of gave up. I don't know how to construct this thing. So I went to Peter and I told him, I see that I have enough matrices to make a transitive action on the building just by computing by hand. And I see that I get enough matrices, but I don't know how to find them for general P. And then he gave to me an old volume and told me this belonged to Selberg, so you have to give it back. And this was Ziegel's lecture notes from 35 explaining the mass formula. And the mass formula is what you have to use, I think, to count the solutions to this completion problem. And it tells you have to count the solutions in QP over all the p-adics and also over Q infinity, which is the real field. And this thing was the big problem for me, because like other people here, I'm like other students of Alex, p-adic analysis I can do, but I've been avoiding this thing since first year undergrad. And suddenly Peter forced me to sit down and compute integrals of real functions, and this is something that I computed, and I think Peter knew that people already worked all these things, but he wanted me to learn real analysis. So I actually computed the mass formula by hand, and then you can count how many elements there are here. But we don't have an explicit description, which is still a big problem in explicit construction. What we can show at this point, for example, so here for PGU3, we have a congruent subgroup which acts simply transitively on the vertices of the building in dimension 3. And this is a very weird group. This is the similar unitudes, unitary similitudes of Z1P when P is 1 mod 4. But you take the subgroup of all the matrices which mod 2 plus 2i are equal to 1 on the diagonal, and anything else you want outside the diagonal. And the weird thing is that I don't see any reason for this even to be a group. Right? But it turns out to be a group, and even a normal group inside this arithmetic lattice. And the proof is just 2 pages of working out computations modulo 2. I have no reason for that, but eventually there is a congruent group, not a principal one, but a congruent subgroup which acts simply transitively on the vertices of the building. Now, now we have another challenge, which is making this fault tolerance. So this is work in progress, so we don't know the final answers, but we already have some exciting things, I think. I want to mention in this context, there is a remarkable work of Cartwright and Steger, which show that in positive characteristic, so over a Laurent polynomial, you have lattices which act simply transitively on the vertices of the building in any dimension. So this is not helpful for unitary matrices. You cannot build, I think, unitary operators with these, but this is quite remarkable. And as with any remarkable mathematical discovery, Alex Lubotsky managed to bootstrap this into solving an open problem in coding theory. So this is a paper of Kaufman and Lubotsky, which uses these lattices to show that You have edge-transitive Ramanujan graph, which give you symmetric low density parity check good codes. So you don't need to know that, but just I think it shows you something about Alex. If there's something interesting, he can do something with it. And I'm kind of done. I wanted to show you the secret of Alex's success. So there has been some rumors here, and a lot of people contributed to the afternoon nap. But the real answer is witchcraft. Thank you.